Okay. All right. Thank you for those who can join this afternoon. So this morning, sorry. And we continue with this topic on the plasma. So I hope my voice is clear over there.
Clearer, sir. It's a good.
Okay. So this is what we have discussed last week on the plasma for nanoprocessing. So we did discuss about how we can use plasma for the etching, for the coating, what are the type of the plasma that is available out there, what was the physics behind that. So in this nanoprocessing, we have to understand about this all this plasma physics, all this the chemistry behind that, and also some surface chemistry because we have the interaction between the plasma and the substrate that we have for the process. And so it cannot move if you have this. And this is what we have discussed. Also, I should. Okay, so we did discuss about this type of plasma sources, whether you have the ICP type or CCP type or magnetron spectrum or the electron ECR or helical plasma. So these are type of high density plasma and low density plasma. And then we did discuss how is the configuration, what is the advantage and disadvantage of this type of plasma system, right? So then at the end, we did watch some video about the ITER, right? The nuclear fusion technology in the plasma. And so for today, I think we have to, first of all, I would like to answer the question that we got from Karishma, Pinka, and Hafid. So are they around? Karishma is here. I can see that. Pinka and Hafid. All right. So the first question was asking about what's the difference between the application of low density plasma and high density plasma. So if we talk about this low density plasma and high density plasma in our daily life, right? So because we have two type of plasma, which is a low density and high density. The low density is the most that we use in the lab or the microelectronic fabrication, and the high density is the one that not likely we have that in the lab, but sometimes we also have that type of in the lab. I will show the example later. And Pinka are asking about the plasma etching. So etching is about we remove material. So how we can determine what is the suitable gas to use for the etching and how to optimally the process runs and how we can know whether the etching process is successful or not. And then Hafid asked about the application of plasma propulsion. Is it just in for the space technology? So that there was the questions. If I got it correctly, yeah, which is from the WhatsApp thing. We got that. Okay. Okay, so the first question about this low density and high density plasma. So we can see in this is the in this graph we can see the density of the plasma in which we use the unit of centimeter square centimeter, which is here is the unit centimeter minus 3 is a cubic centimeter. And then here is the temperature of the plasma in the electron temperature. Normally, we measure in a volt. Okay, the unit is volt. So in this range is showing the high density plasma is in this region, the high density plasma, where this is a low type of plasma. And of course, we can also differentiate the plasma in terms of their temperature. So we can see the solar wind, the aurora, for example, that we can see on the sky, that is a type of a very low density plasma actually and low temperature. So our pentafloor lamp at home is also a type of plasma, as I mentioned last time. So it's a low density and low temperature plasma. And most of the low pressure, low density plasma is the one that we use in the lab for the microelectronic fabrication. But for high density plasma is something like plasma focus, laser plasma, shock tube. This is some type of arc plasma. So the example is on the right, which is the plasma that they use it for the welding application. So high density plasma for a plasma welding. So you can see in this figure how they put the gas inside they have the electrode here. This electrode connect to a very high voltage. And then you have, so this electrode made of a tungsten. So it can stand a very high temperature. So you have a gas and also the water cooling. And then that one where you have the orifice, so they have a very high density plasma like this. So you can see very bright. So if you want to know the plasma is high density or not high density, most basic way is by just see the plasma itself. So you can see very bright here. So this is you cannot see by your naked eye. Sometimes it will hurt your eyes. So that will be a very high density plasma. So high density equal a high temperature as well. So equal, that's why it can be a very, it can melt the metal so that it can be used for the welding application. So this is the example of a high density plasma. They use it for the welding application. Okay. Then another example where they can use a high density plasma is on this one. This is we call as a so this is another way why they use high density plasma to produce an X-ray or some UV light. So this plasma they produce is a beam, a very small beam. They are using a laser into the material, some target, and after the laser hit the target, it will have a very bright plasma region over there. So that plasma will contain a EUV, the extremely ultraviolet emission. So that extremely ultraviolet emission is very long, very short wavelength, which is maybe around like 100 nanometer, for example. So a very short wavelength. So this EUV is very short. This wavelength. So maybe like 100 nanometer in their wavelength. So this wavelength they will be used for lithography process. Lithography process is a process for they use it for the etching. Before they do the etching process, they need to use the lithography process to do the patterning, the design of the pattern on the wafer. So this EUV, they have a very sophisticated mirror for this processing. And then at the end, they can do the very fine, small pattern on the wafer. So this is another advanced technology of photolithography, actually. So this is the basic of photolithography. So the common photolithography, we just use this using the UV light. So UV light maybe in the range of like, well, is below than 400 nanometer, maybe like 200 something nanometer, up to 400 nanometer, right? So that is the range of current UV light. But of course, when we want to scale down the device of our electronic device, so we need to put more chips. So you can see the Apple right now, for example, the new iPhone, they are using the technology of like a 7 nanometer of technology of chips. So to make this small chip, you cannot use this conventional UV light. So that's why they have to go for the EUV, for which is smaller than 200 nanometer for the lithography process. So to make this new chip, actually you have to go for this kind of technology, which is EUV. So this is another example of high density plasma. So they use it for the fabric to get the source of UV, which is the extreme UV. Okay. Okay, if we talk about the low density plasma, so the low density plasma, as I mentioned in the previous lecture, we use it a lot for this plasma cleaning application. You see that they put the glass inside the plasma. You can see the plasma is also very mild. You can see with your naked eyes. So we can see there's the plasma region that do the cleaning on the glass here. So this is one of an example. We use it for the plasma cleaning using the low density plasma. And on the right, we can see the chamber having some low density plasma for the plasma etching as well. So you can see inside here. So it's very interesting. It's very colorful to see this plasma actually. So during the etching, what will happen is that, this is the cartoon showing all the element that you have inside the plasma. So we have the ion, for example. You can see here the ion positively charged, and then we have the electron here. Okay, we have the gas molecule right here. So okay, and then the ion will hit the material of the film, for example, and it will remove that. Okay, so the resist is an area that we don't want to remove. This is the area that we don't want to remove. So we put some cover, some blanket. The area that we don't want to remove is here, and then the area that we want to remove, we expose to the plasma. So if when this area is exposed to the plasma, so the plasma will react with this region, and then it will remove its material. Okay, so this is what we call as a plasma etching. So this is the most basic process that will occur in this etching, which is used for the microelectronic fabrications. So most of the time, the silicon is used as the substrate here. Okay, so then here in the film, sometime here, most of the time we use silicon dioxide, and this photoresist is some polymer for the photoresist. You can see my writing, right?
Yes, sir.
Okay. If my explanation is not clear, please interrupt me. Okay. So that was the question by Karishma. Is it okay, Karishma?
Yes, it's clear, Prof.
Okay, thank you.
Thank you, Prof, for the answer.
Okay, no problem. So thank you for the question as well. Right, so we go for the next question about Pinka asking about the plasma etching. So we did discuss about just now that we can use plasma for the etching. Okay, I can use it for the to remove the area that I think I don't want. If I say that I have a silicon wafer and then I have the silicon dioxide, so I want to do the patterning, I want to remove this some portion over here, so I do the etching process, right? So to remove the silicon or silicon dioxide, what are the gases that we can use? So this is the question, I think, by Pinka. So what are the suitable gas for specific etching application? So these are the table showing the material and the gas that can be used. So for example, if you want to remove a silicon or amorphous silicon, you have to use a CF4, SF6, and BCl. So which is the fluorine base and the chlorine base. Okay, so these are the gases that will create a plasma. So, and then I think that I will show this chemical reaction later on. So where you create the F actually. So that F actually will react with the silicon, and sorry, should be a plus over here, and then it will create a SiF4. So you have 4F, they will react with the silicon, and then we create this SiF4 in the form of gases. So that gas will pump out. So that's why we can do the etching process. So different gas will react with different material. Okay. So if you use a CF4, this material gas, it will react for the silicon. If we use this material, the combination of fluorine with the oxygen and hydrogen, it will react with this element. Is for nitride element, we have to use these gases. And for gallium arsenide, so you have to use a chlorine base. For indium phosphorus, you have to use this gas. For aluminium, you have to use a chlorine-based gas. And for some resins or polymer, you have to use oxygen gas. So we can create the oxygen plasma as well. Okay, how we can estimate? Okay, for example, if we have like like this silicon etching here. Okay, let me erase this one. Okay, for example, if I have the, right now I mentioned that I have a silicon wafer here. Okay, the thickness of silicon wafer maybe like I say like 500 nanometer, for example. And then if I have the silicon dioxide here, 200 nanometer. So this is the thickness. I'm drawing a cross section, the cross section. So if my silicon dioxide here, SiO2 here, is a 200 nanometer, so I need to know what is the etching rate for my material. For example, if I want to etch a silicon dioxide, sorry, so if I want to etch a 600 nanometer, since my etching rate here is a 500, this is 500 Armstrong per minute. So if I convert this and calculate, right? So because in 1 minute, I can remove 50. So to remove 200, I like 2 times 4, right? So I need approximately like 4 minutes to remove this 200 nanometer thickness of silicon dioxide. So this is what we call as etching rate. So this value is something that most of the time when you buy the equipment of plasma etching, they will give you the recipe or the it depends. It still depends. That's why we can see they mentioned here it's approximately 500 Armstrong. This is the unit of Armstrong, so you can convert it to the nanometer. Okay, so it's about 50 nanometer per minute. So, but of course, this is approximate number, but we can use this approximate number in order for us to estimate what is the time for the etching process. So it depends on the gases, it depends on the material. For example, here side you have a so just now it was a silicon. This value actually is available when you buy the product, when you buy the machine. So they will optimize the value for you. And sometimes in the lab, in our lab, for example, I think Dr. Go also can do the same thing. When we develop our own plasma system, when we develop our own plasma machine, we have to do the optimization, for example, and then I do the etching for 10 minutes. After 10 minutes, I see how much is the silicon dioxide removed. And then I do again the same experiment for 20 minutes. Okay, so after I do 10 minutes, 20 minutes, or 30 minutes, 20 minutes, 10 nanometer. For 30 minutes, I move 20 nanometer. So by having this value, actually I can do the plotting of my own etching rate, right? So I can draw a graph, something like this. So this is the etching thickness. This is the time. So by having 10 minutes, I can know what is the parameter. 20 minutes, I can get one more parameter. 30 minutes, I can get one more parameter. And then I can get plotting a graph over here. So by having a gradient between this curve, so I can know what is the etching rate. So how many nanometer per minute for my own plasma. So for those who develop their own plasma, we can do this kind of analysis in order to understand what is the etching rate of our system. So we can our own actually this one. So that's how we can understand what is the time that we can use for the etching. So how to confirm whether the etching is has been successful or not? So this is another issue. So as mentioned, you can see the gases will only react on the specific material. So this gas will react for the silicon. This combination of gas will react on the silicon dioxide. This combination of gas will react on silicon nitride. So if we have a silicon dioxide, sorry, maybe should. So if I have the silicon dioxide, O2, and I have a silicon at the bottom, so I only can remove the silicon dioxide if I use this gas. So it will react with the silicon dioxide and it will stop at silicon. So it will no more continue to react with the silicon because I have the other gases. So that's how we can understand actually, because this is what we call as the selectivity. So the gas will react only with its targeted material. So it will not remove another material. So that's how we can understand that the process is already successful. So we need the time. We need to know the time, and then we need to know what are our base layer. So when we know both, we can know that after this certain time, it will react until the end of the process, and then it will not more react with the other material underneath that material. So that's how we can understand, right? So if you can see the here in this table also, I can we show the some other material and some other action atom. So for example, for the silicon and germanium, so we need a fluorine base and chlorine base. Silicon dioxide, we need a fluorine base. And see other metal like aluminium, like copper, we say we need a chlorine. So this is the most common for metal. Some other hard metal like tungsten, tantalum, titanium, we need a fluorine and a chlorine base. So for the gold, you can use a chlorine. So some other material, yeah, these are the gases that we can use. So different material, different gases, and you can see that we can do a lot of uh, etching process. It depend on the gas, and the issue is the gas is quite expensive actually. So if you want to buy the gas for the etching, is very expensive. For example, because most of this is a very rare. I'm not sure whether it's produced in Indonesia or not. But even in Malaysia, this type of gas is not produced. We have to buy it from overseas. So it will take some time for us to get the gas in-house. So this is the issue. So did I get Pinka clear?
So the gases is absolute for specific material like that.
Magnet, what do you mean?
The gases is absolute for specific material.
Yeah, your voice a little bit delay, but if I understand it correctly, yes, specific material is you need to use a specific gases. Is that your question?
Oh, okay. I got the point. Thank you, Prof.
Okay. Thank you for the question. But anyways, so etching is a very crucial actually in semiconductor industry. We can see even you can be a very expert in this etching process by understanding the etching reaction, the etching parameters. So in all semiconductor industry, they have to have this process engineer. In the semiconductor industry, we call it as a process engineer. So by understanding this etching process, I think it's very good if you can understand it, and it will be a good point, selling point for you to secure a job in this semiconductor industry actually. Okay, so I move to the next questions. Okay, again. So this is another information about the etching actually. So what we have here is okay, the most basic process of the plasma is that we have in the plasma we have the ion will bombard the material and will remove the materials. Okay, so that one we call as a sputtering. And then we also have neutral, and also the volatile product will do the etching. It will remove the chemical. They have a chemical reaction. And then sometimes you have the neutral and the ion also will react the sample. And sometimes you have the neutral ion, and then you have something that to prevent the material. So this is also etching. So I mentioned just now about the selectivity, right? Selectivity. So selectivity is the process where you have the because we have the silicon dioxide or silicon here, and then our fluorine gas will react with the silicon only, right? So that is in the case of we use gases only, but in the plasma we also have some ions also. Some ion, that ion will do a process of we call as ion bombardment. So since we have this ion bombardment process, so even though we have the photoresist area here to cover the area that we don't want to do the etching, sometimes the photoresist due to this ion bombardment process, the photoresist also becoming smaller. It becomes something like this after the process. Okay, after this process. This is because of the ion bombardment process. It will remove the photoresist material by the sputtering phenomena. So for sputtering of the photoresist. So that's why it's very important also to make sure that the thickness of the photoresist should be thick enough to sustain the time. Because for example, just now we calculate we need like 4 minutes for the etching. So make sure that the thickness is thick enough to sustain the 4 minutes of ions bombardment sputtering. So normally in this, the photoresist with in the range of like maybe 20 micrometer or thicker. So it's in a micrometer range. It's a micrometer range. Whereas this is for the photoresist, or in short, we call as a PR. PR. So the short form that we use for the photoresist is PR. And the film normally that we process is normally in the range of a nanometer. So that's why by having a PR at a micrometer range, it's easier for us to control, to do the etching on the nanometer range. So our PR should be micrometer. So these are the chemical reaction actually, the one that I mentioned just now. The silicon will react with the fluorine, and then you get the SiF4 gases. So that's how the chemical reaction occur in the etching process. So these are some other examples of how the fluorine in the gases react with the silicon, the solid here. This is the solid react with the gas. Okay, so that you can do the etching process. So how to get this fluorine? Fluorine, because we have the CF4 gases, right? CF4 gases, it will create the CF and C and F will just separate away. So because of the plasma, so that's how we can get the F. So that F will react with the silicon, and then you can get the etching process. Of course, you guys is a chemical student, so chemistry should understand much better than me, I think. So this is the etching. So okay, we can also see this is another example how we can actually know that the material that we want to remove and the gases there. So most of the structure etching of if you want to use platinum or some material, so we can use this argon gas. If you want to do the cleaning and to remove the PR, so remove the PR, actually you can use this oxygen and fluorine based gas. Etching also remove so PR removal, you can use also the oxygen. So these are the the material, the material and the gases that we can use. Okay. Okay, then Hafid asking about the plasma propulsion. This is a different different topic actually. Plasma propulsion is a different technology where people want to explore this one for the, we call as a new technology for the space application. So as what is asking about this, whether it's just applied in the space. Yes, it's the only technology I think they apply for the space technology, and it can be space out of the earth, and also our aerospace for the airline fabrication for airline industry as well. So they want to use this plasma propulsion for the small satellite. So you can see the picture here. So we can put this one on for the satellite, so that we can move around the satellite, not only on this its orbit. So we want to control it. So on the satellite, we cannot use a chemical reaction of rocket engine, because you have to make sure the rocket engine or the hydrogen, the fuel, is on the satellite. So we cannot have that one, right? So what we need to have some electrical powered engine on the satellite. So that's why they have proposed this kind of plasma propulsion, because you can produce the plasma by just having the electricity. So how to get the electricity? Of course, they can get it from this kind of solar panel, right? So that's how we can use plasma for this satellite application. So so we can use it for the satellite. We can also use it for the engine. So you can see currently they are developing this kind of plasma jet engine for the aerospace application. So we can make sure that in the future we don't have to use the carbon or the oil fuel kind of source to create to burn our engine. So they want to use some electricity, so that maybe later on you can have electric powered aeroplane in the future. So since you have the sunlight on the out there, so it's easier for you. So meaning that you have a lot of source of energy to create your own your plasma jet engine. So in this will be in the future. So we're not sure when it will be available in the market, or so whether it can be realized or not. So we can also see, so they want to use this plasma propulsion as a new way that we can fly to the Mars. So the NASA is working on that. They want to launch a super fast trip to Mars by using a plasma propulsion. So maybe our grandson or you guys son or children later on in the future maybe will be able to go to Mars by having this space shuttle in the future. So you can see some, I wonder if you guys know about Elon Musk. So he's a very famous person that tried to create a lot of technology, and they want to use it even for the space industry, right? So you can see how you want to reach Mars by using the plasma engine actually.
Nuclear donut for Elon Musk, or the engine that will deliver a mission to Mars.
Can you hear that?
To figure out how to populate Mars, you need to have the mind of Einstein, the wit of Louis C.K., and the courage of Captain Jack Sparrow. The inefficiency of rocket engines still remains the main obstacle. Chemical propulsion systems are
Oops, sorry. We will stop just now.
nuclear. In other words, they cannot maintain traction for a long time due to the rapid fuel consumption. It's one thing to go into orbit. It's quite another thing to make an interplanetary flight. There is nowhere to refuel in outer space. A few words about the unusual approach of Musk's company. This is really interesting. Usually, computer simulations are carried out before launches, and only after that, prototypes are tested. NASA doesn't like explosions. Musk has a different approach. SpaceX produces prototypes of varying levels of readiness with the MK and SN indexes for testing specific technologies. For example, Starship SN2 was created to test the structure to which the engines are attached, and the SN5 was launched with one Raptor SN27 engine, but without the fairing. This explains the unfinished appearance of the rocket, but the SN10 had 3 engines. Things NASA tried to hide from the public eye were turned into a show by Musk. We're talking about the Interplanetary Transport System. In-orbit refueling is a key element of this system. The algorithm resembles a computer strategy game. The first rocket launches a ship with people into orbit. The next to go are tankers with fuel. After refueling in orbit, the Starship will be able to go on an interplanetary flight. Science fiction is getting closer to reality, but if a new type of propulsion system appears, then Musk's idea loses all meaning. While physicists were thinking about creating a propulsion system, NASA developed a strategy for the development of the Red Planet. The plan of a person's stay on Mars from the first day until the opportunity to have visitors there is developed in sufficient detail. In general, the colonization strategy looks like this. The first ship delivers a 3D printer to Mars. At the next stage, the 3D printer creates the individual elements and components of the future stationary engineering structure. The building materials are soil, water, rocks, and atmospheric gases. One of the tasks of the Perseverance rover is to collect samples of everything on Mars. After that, the printed parts are assembled in the correct order, and voila! We have a full-fledged Martian base, capable of receiving people and cargo from Earth. That's what we meant when we talked about WIT, delivering a small 3D printer that will print a bigger 3D printer, and so on. But seriously, 3D printers have already been successfully tested on Earth and aboard the ISS. Experiments have shown that these devices are capable of printing almost everything that is necessary for the life of colonists on Mars. This will be more efficient and cheaper than delivering everything needed by space shuttles. The only difficulties are energy sources of appropriate capacity. And these, as you might guess, are the main component for the life support of the base. By the way, a 3D printer also needs energy. It turns out that our civilization has no alternative to nuclear power units. The 3 most common concepts of a nuclear rocket engine were known until recently: solid phase, gas phase, and liquid phase. Each type corresponds to the aggregate state of nuclear fuel: solid, melt, and high-temperature gas or plasma as its alternative. A solid-phase nuclear rocket engine is essentially a nuclear reactor, or a chamber where a nuclear reaction takes place. The fuel element is rods or hollow tubes. Uranium dioxide pellets sealed inside each rod are the fuel. This is how most stationary nuclear reactors work. The nuclear reaction of uranium dioxide heats the rods, which in turn heat the medium, or as nuclear physicists say, the working medium of the reactor. Hydrogen is usually considered a working medium for a solid-phase nuclear rocket engine. Less commonly, it's ammonia or helium. Let us recall that water vapor from heavy water is the working medium in nuclear reactors on Earth. Compactness is important for a nuclear rocket engine, so hydrogen is acceptable. Turning into gas, the working medium breaks out into the nozzle and thrust appears. The specific impulse of a solid-phase nuclear rocket engine is 3 times higher than that of chemical rocket power plants, and is about 800 to 900 meters per second. For example, SpaceX's Raptor engine used for the Starship has a specific impulse of 380 in vacuum and 330 at ground. For liquid-phase jet engines, where nuclear fuel is in a liquid state, The impulse is 14,000 meters per second. In a gas phase or plasma nuclear jet engine, the impulse is even higher, 30,000 meters per second, which is 10 times more than that of chemical analogs. However, working models of
Okay, so sorry about that. So we can see that in the future there will be this kind of the plasma that machine that will be used for the future of the Mars exploration. So in short, we can see that plasma propulsion is the one that technology that they will use it for the future of space exploration. That's the only way of using plasma propulsion. So there is also some technology about the plasma engine for the car, to enhance the plasma combustion inside the diesel or gasoline engine. So, but this is also under research, which is not available yet in the market. But that's will be the future, right? So I hope I get I think this question by Hafid. Is it clear, Hafid?
Yes, Prof, clear enough.
Okay, thank you. So I think we want to touch a little bit on the fundamental of the plasma. What we can see inside the plasma. Okay. So okay, these are some of the value that you will see when you read some of the textbook of the plasma. So I think you guys know most of the constant or the symbol that you can see here. For example, you can see like we have the Boltzmann's constant here. I think most of you guys know about it. The electron charge over here, the electron mass, the proton mass, the mass ratio, the Planck constant H here. I think you guys use this in a lot of your subject. Speed of light in a vacuum. So permittivity in the space, permeability in free space, pore radius, atomic cross section, temperature for 1 eV. So this is for 1 eV. 1 electron volt equal 11,605 Kelvin. And you have Avogadro number. Okay, you have the gas constant for the unit. So these are the value. I think that you guys are very familiar with it. So this is also some other value, which is like the standard temperature. 25 C is almost like 300 K. 1 Pascal or one atomic pressure is equal to 1.0133 times 10 to the power of 5 Pascal. So which is also equal as 760 torr. So sometimes we use in the unit of Pascal, sometimes we use the unit of torr. So, and then this is not very easy. So, and one pressure at 1 torr, for example, and these are the unit of energy. So these are the value that if you find, you will find when you read about the plasma books, textbook. So plasma as a reputation is very difficult to understand because of what? Because of the of its complexity, because most of the time we can see in plasma we have the atom, we have also the ion, we have also the electron, the negative electron. So all of these have a charge, So when you have a charge, you have something that will repel. Sometimes they will go together, right? So this make it more complex. So this is probably true when we compare with the fluid dynamic and electromagnetic in the dielectric. So it's not only a fluid; it's also a electromagnetic. So it's being a charged fluid, plasma particle interact with one another, not just by the collision. So you have a lot of interaction, the chemical, also the physical, and the electromagnetic interaction over there. So the field is in the plasma is modified by itself, and the particle can move to shield one another from the imposed electric field. So because of this is this is a charged particle. So when the charged particle move, they will create some electric field. So that electric field will be covered by some other particle that have a charge, right? So that's why when you have a when inside, it's not just a common gas that moving around like gases, right? So if you have inside one chamber with a gas, so it's much more easier. But you have inside here is some electron, some positive ion, so they are moving around, and this reaction is make it much more complex. So, right. So most of the plasma is too tenuous and hot to be considered as a fluid. For water, it can be in this density. So air in this more density, with the particle density of the plasma is much less. Okay, 10 to the power of 9 to 10 to the power of 13. So that's why it will not always react as it will not always react as a continuous fluid. So that's why it's different. So this is 10 to the power 9 to 13. Where else you can see the water is in this range, the air or the nitrogen, the thing that we breathe every time. So in this value. So in the plasma, the density is much lower. So the discrete nature of the ion and electron make a difference. So this kind of detail is treated in the kinetic theory of the plasma. Okay. So you can, as mentioned, this I showed this figure last time. So this is a plasma in the lab. So most of the time you can see the density inside this plasma is in this range. So argon ion is 6 times 4 times 10 or 10 per cubic centimeter, whereas the chlorine ion is 1.5 times 10 to the power of 11. So this is the modeling. You can find it. You can see just the figure, the cross section of the plasma, high density plasma at the center. And this is the coil. Actually, this is the coil, the ICP coil, for the plasma induction. So this is type of ICP plasma. So one of the basic understanding or fundamental that we have to understand in the plasma is about this quasi-neutrality and a dipole length. So the electrical and magnetic field in the plasma control the particle orbit. At the same time, the motion of the charged particle can be a charged bunch. So it creates the electric field and also a current. Okay. So as mentioned, we have a lot of particles. That particle will move around. So when we move around, we create electric field and also there will be a current. So and then we create a magnetic field. Okay. So that's the portion of particle motion. The electric magnetic field has to be solved for its self-consistent way. So we use the Maxwell equation, the Poisson equation here. So divergence of D is under this value. So we have E, divergence of the magnetic field, electric field here. So then we have a ion and also the electron here. So this equation actually is come from the Maxwell equations. So the divergence of this electric field is should equal to the difference between the field inside here. So because you have the ion and also electron, this is for the ion, this is for the electrons. So of course, if Ni equal Ne, so the number of ion and the electron is equal. So this is this is the positive, this is the negative. So this will be neutral, right? If the positive and negative is the same, so that will be neutral. But if Ni is less than Ne or Ni is larger than Ne, so it will not be neutral. So there must be some field. So because the electron will move to the, so if we have electron, will move to the, when you have a positive side here, so we try to move over here, so we create some field between these two regions. So this is the, if we look into this small region, this is the sum which is not neutral. But if we look into a larger area, if we look outside of it, so it will become Ni equal Ne. But if we look micro, if we look small, so it will not become Ni equal Ne. If we look at this region, for example, this is not Ni equal Ne, right? So because we are looking at a very small area. So this is the difference. So we need to understand that. So having this equation, so we can use it for the, we can expand it that, right? So if you know that the electrostatic field here, E is also can be derived from the potential of the voltage. So this is E equal the diversion of this voltage potential. So then we can substitute this into the equations. Thus, we can have the divergence of V is equal to the difference between the electron and the ion here. So that's how we can get this equation 2. Okay. So from the equation number 2, actually we can just try to invert just put the value of diversion here to become here. Okay, we just replace the diversion with the IL, which is L. We refer to the length of the anything that we have in the plasma. For example, the length of the distance between two atoms. or the length between the, okay, so this is the length between the, for example, if we have the positive charge here and the negative electron here, so this is the length, the distance between the two particles. So if we talk about the electric field and the thermal energy of KTE, so you can get this KTE and the L into these equations. So we can define this L, or the debye length can be defined by this value. So which is the delta. So we put the delta as a, this value KTE, and so if we define delta as this value, actually we can replace this to these equations. So that's why we can get this EV and also the L and the lambda here. So lambda as a function is a value that we substituted from here. So having this lambda, we name this lambda as a debye length actually. So indeed with this lambda, we can actually evaluate the length of the distance. So I'll show you. Okay, so since the value of we can know the value of epsilon and also the electron. So that's why we can actually simplify the value of lambda d. So at the end, it becomes 7.4 square root of TE and also NE. So TE and NE is this is the electron temperature inside the plasma. And this is the density inside the plasma, the electron density. So from this equation, so we know that the debye length, or the distance between this particle inside the plasma, is dependent on the electron temperature and the electron density. So the higher the temperature, meaning it can go very fast, and then it can go very separate away, right? So we know that because of the motion of the gases and also the particle inside it. So the higher the temperature, so the distance become higher. But the higher the density, the distance become shorter, because we have more particle confined into one area. So you can see it. So that's why this distance become shorter. So this is the example. You can see the lambda is in the order of 50 micrometer. If the KTE is 4 electron volt, and the electron is 10 to the power of 17 or 10 to the power of 11 per cubic centimeter. So in this one using a meter. So if we use it 10 to the power of 11, or you can 10 to the power of 17 for meter cubic. So you can put it into this value actually, and this KTE is here, electron volts. So actually you can get the distance between the particle is around 50 micrometer. So this how actually we can also try to calculate, if for example, if we have the pendant floor lamp, right? The pendant floor lamp at home is around 1 EV, and the density maybe like 10 to the power of I think almost the same, maybe 16 cubic meter, something like that. So then we can know what is the distance of the particle that moving inside the plasma. So I put this as the homework. Maybe you guys can try to derive equation this 7 from the from this previous one. Actually, you can just substitute the value of epsilon and electron here. So from this equation, actually, from this number 5, you can just substitute epsilon 0 and the E here. So actually, you can come to this conclusion. So I put this as a homework. So maybe you guys can try it later on, and you can just submit it to me. I will share the email address, or maybe I will create a Google form for you guys to submit. Okay, is it clear?
Yes, clear, Prof.
Okay. All right. So so this is the condition where we want to understand whether the particle, whether the ion and the electron have a distance, or they are neutral, or they are equal, or they are not equal. Okay. So in the case, most of the case, inside the plasma, we say the plasma is a quasi-neutrality. Okay, because the number of ion and the number of electron is almost the same. It's almost the same. Yeah? So it's almost the same. So that's why we call it as a quasi-neutrality, and it's probably the most important characteristic of the plasma. So the charged particle will always find a way to move to shield out the large potential and maintain the equal density of the positive and the negative species. So if you have a very big particle inside it, positively charged, what will be the electron, the small electron will do? They will try to move it there, right? They try to move to the big positive particle that you have here. So of course, when the electron move to this particle, what will happen? The remaining area here, the remaining area will become positive, right? Because the electron go away, so the remaining area become positive. Then it will take another electron to come to this area. Okay, then until a certain time, the electron here, all the electron is covered already. Another electron will come, it will repel away, right? So this is what will happen. Another electron come, it will repel away because we have the electron inside here already. So that is the problem, where you can see that sometimes you will see the electron here is not as the same as the positive ion here. So that's why we call it almost the same value. So Ni almost equal to the Ne. So this is a quasi-neutrality. So you can see this is the difference. What you can see, sorry, my children shy. All right, so then you can see the, okay, what if we have the ion with the charge of Z? Okay, the condition of neutrality is simply Ni is to the number of Z and E. So what's that mean? For example, our ion is we have argon 2 plus. Okay, so the most basic one is argon plus. So then argon plus, how we can get is because of we release one electron from here. So if you have argon 2 plus, meaning that you need to have you have extra 2 electron from this one, right? So that's why the number of N ion is equal to the Z of Ne. So the number of N argon 2 plus is equal to the 2 Ne. Okay, so the number of argon 3 plus, for example, is equal to the number of 3 and E. Okay, so that is the condition of quasi-neutrality that we have to comply. So because it's a simple reaction, argon plus the electron, get the argon plus the 2E. So this is the simple chemical reaction when you want to express the ionization, right? Okay. The class should be until what time? Somewhere around another like 15 minutes, right? Okay. Okay, so when you have a quasi-neutrality inside the plasma, so we can say that the potential inside here, inside the plasma is equal to 0. Okay, so because we have the Ni is almost to the number of Ne, so there is no potential. So meaning the potential V is 0. So, but the issue is on the border, at the border of the chamber. Okay, at the border of the chamber. So this is the chamber, which is that contain our plasma. So at the border, this chamber is grounded, right? We put into the connect to the ground. So because of it is grounded, the electron prefer to go there and go to the ground. So then that's how the electricity will complete its circle inside this plasma. So in this condition, there is a region where we call as a schist. So schist is a region adjacent to the surface, and the schist is a thickness about 5 lambda. Okay, so this is an important value, 5 lambda. We did calculate the value of lambda just now. So this is the bi-length, lambda d. So lambda d is times 5 is we call as a schist. Schist is a region here where you can see it is not neutral. The Ni is not equal as Ne. We know the argon, as I mentioned, argon plus will react with the electron. You will not argon plus, argon will react the electron. It will create argon plus 2 electron. Okay, so you have argon ion here, and you have the electron here. Which one is lighter? Which one is heavier? Argon and electron. So the argon should be a heavier one, because we know if you have the atom, surrounding it is the electron, right? The small electron is surrounding it, right? So you have the orbit, and then the electron is surrounding it, right? So electron is much smaller than the nucleus of the atom. So if we have the argon ion here, argon ion is because we have one electron go out. So that's why we have the argon ion here. So this is the electron. This is the argon ion. So the argon ion is much heavier and much larger compared to the electron. So you can see because of the electron is much smaller, it will go very fast to the ground, and it will make that the ground is become negatively charged. Okay, So when the ground here is negatively charged, we have many electrons here. So later on, when another electron want to come here, it become repelled. So because of the negativity that we have here. So for the because of the negativity that we have here, so the argon ion will try to go to the negativity that we have here. So that's why you can see the argon ion will try to hit the target, and electron will go here much faster. So it become much electronegativity here. So the argon will go back there very slowly. So because of the slower ion, so it will keep the plasma quasi-neutral. So that's why some of the plasma, the ion will remain in the chamber. So that's why you can see that you have the ion and the electron inside the chamber as a neutral. So this is a schist. So this is we call as a schist region. So in which the ions outnumber the electron and the strong electric field is created. Okay. So this is some fundamental to understand what actually inside there in the plasma. We can see this schist region actually. So this is another example to show the electric model of the plasma boundary. You can see when they try to do some modeling, and they can know what is the region of the schist and then the potential of the voltage inside here. So just okay. So let's think ourselves as the ion inside the plasma. So what you will see is that when the ion try to approach a schist, so you will see something like this. You will see a very sharp down region at the end of the wall. So that's why you can see when the ion approach the schist, it is facing this phenomena. But sorry. So this is the ion. When the electron, when this is the ion actually. So this is the electron. When the electron try to approach the schist, it will face this kind of phenomena. So, but if we for the ion, it will become very much slower because ion is very much bigger, very much heavier. It will go very slowly. But the electron, it will go very fast. It will face this kind of field inside the plasma. So in fact, we can see this phenomena or this situation very clearly in the lab. So this is the wall, and down here is the plasma. So you can see a clear border. So where the electron go very fast to the wall, and then you can see the ion will keep inside here. Let's say it's argon, so we'll keep the argon inside the plasma. So of course, at the same time, we also have a small number of electrons inside here to make sure that the number of ion inside here is equal to the number of electron. But this here is not, it's not equal. Okay, so you can see the wall is we have a dark region over here. So that's why you can see the boundary between the plasma and also the wall. So this is to make sure that if all the electron we move to the wall, what will happen? There will be no plasma because there is no charge that contain or inside the chamber. So all the electron will move to the chamber, and then there is nothing remaining inside the chamber. So that's why you can see here that will not happen. But for the plasma, there will be some schist region that will make sure that the plasma is sustained. So this is we call as a schist region to make sure the plasma is sustained. If not, you cannot sustain the plasma. So that is a very important phenomena inside the plasma that you will see. Okay. So again, this is how you can see the cross section of the potential of the plasma and also the Debye length, the schist region, and then this area actually we call it as a pre-schist region. The area here we call as a pre-schist region. The area here we call as a schist region. This is our wall. Okay, the length here we call as a Debye length. Actually, this is 5 times of a Debye length. So Debye length we can know it from the electron temperature and the electron density. We can calculate it, so we can know what is the approximate thickness of this region actually, how many micrometer, okay, or maybe like millimeter, okay. Okay, a very short one. So it's mentioned just now we are talking about something that is at the wall, near the wall, in the wall of the plasma, between the plasma and the wall. So inside the plasma, we not only have a wall, so we have a chamber here. So this is our chamber. So this is our plasma. So the region between here we call as a schist. And then we need to understand the Debye length. And then we need to know that the electron inside here is equal to the ion. The region here is not equal. Okay, sorry. Okay, so what happened inside this plasma when we have an equal number of electron and ion inside here? So there will be a lot of collision, So this collision, it can be elastic, it can be inelastic. So what is the difference of elastic and inelastic collisions? It's something like this, right? It's a simple way of showing the elastic collision. So where the energy on the left is preserved, where when you move, you hit and then become separate away. So kinetic energy is conserved. What for the inelastic condition, the kinetic energy is not conserved. So this is another example of elastic collisions, and also the perfect inelastic. For example, when something that hit the wall stick over there, so where the energy after that is equal to 0. So that is a perfectly inelastic condition. So for the elastic condition, the energy is preserved. So inside the plasma, so we can see a lot of reaction actually that we can write down here. So this is an example of the most basic one is an electron that hit with the atom and then become an elastic collision, just go away without no any phenomena occur. But most of the time, you can see a lot of electron impact ionization. So this is an example. If I have the argon atom here, you will hit by the electrons. So then you will hit you get another 2 electron out from this orbital, and then the first electron will still go away, at low energy. So maybe this one is a very high energy. This is a low energy. But you have a argon plus electron become argon ion plus 2 electron, right? So this is the basic of electron impact ionization that will occur inside the plasma. And we can also have electron impact excitation. So where the high energy electron hit it, so what will happen is just the electron inside the orbital of the atom we jump to the higher level of orbital. So it just excited to higher level. So argon atom hit by the high energy electron, it become argon excited state plus the electron. So in the excited state, maybe this one is a ground state. Ground state is 0 eV. Maybe the excited state is like 11 eV. Okay. For the argon to become argon ion is around 13 eV. I'm not sure if I remember it correctly. So it's around 30 eV, for example. You need 30 eV to ionization. But if the energy here maybe like only 11 eV, what will happen is that we just excited. So the electron inside the atom, we just excited to another level. So that's why we can get this argon at the excited state. So this is what we call as electron impact excitation. So this is also occur in the plasma. So you can see another process, electron impact dissociation also occur. So how this we can make correction for this one. Let's see, for example, I have like N2 nitrogen react with the electron, and then I will get another N plus another N plus electron. So this is what we call electron impact dissociation. I can also have a electron metastable ionization. So example, I have one atom at the excited state, mentioned here. So for example, I have argon metastable at the excited state. I hit with the electron, and then I can get argon ion plus 2 electron. So this is what we call electron metastable ionization. Okay, it can also get panning ionization. Okay, panning ionization is something that you hit the little bit difference where because you don't hit by the electron actually. So what happened here is you have the argon at metastable state plus argon at the ground state, and then you got argon plus another argon plus electron. Okay, so the charge is conserved. So because of this high energy, for example, like 11 eV, it will hit this argon so that it become ionized. So maybe the argon is here is another high energy here. So then you become ionized like 30 eV here. So this is like I'm not sure how, maybe some low energy. It should be conserved. So this is elastic collision. So this is what we call as a panning ionization, where you use the high energy metastable element here to do the ionization process that we call as a panning ionization. And then we can also have a de-excitation, where you have the excited state electron inside the atom, but what will happen because of the electron is not stable over there, it will go to the ground state, so you emit some emission, HMU. So this is what we call HMU, the emission. So the atom will go down to the lower state, and then the energy is released in the term of a photon. So that's why you can see the emission. Okay. So we can also have a three body recombination like this. So you can have some other elements try to hit with the electron, and then so what are chemical reaction that will occur for this one? For example, you have the argon here, argon plus here, hit with the electron, and then it will recombine. So the argon become argon. So the electron here combine with the argon ion here, it become a neutral argon. So then neutral argon. So this is what we call as a three body recombination. So you have three body here, and it help in order to recombine the argon ion become argon. So this we call as three body recombination. You can also have a three body recombination in terms of just from the radiative process. So you have the argon ion here plus with the electron, and then you get the argon neutral, and then you emit some the balance of energy by in terms of a photon here. Okay. So this is the last, I think. So you can see electron attachment as well. So the chemical reaction, that's something like this. You have the atom here, and then the electron will hit the atom and then will attach on that. So we call it as an electron attachment. And you can also have ion recombination. So where you have the neutral positively charged atom here and the negatively charged atom here, it will recombine and become a neutral. So most of the case for this one, we can see inside the oxygen plasma. So we can see the oxygen plus hit with the oxygen negative, it become oxygen plus oxygen. So this is the ion recombination. Okay. In summary, plasma is still an interesting tool for the future. So plasma processing is a complex correlation between plasma physics, plasma chemistry, and the surface. So you can see a lot of chemical reaction that we can see, a lot of calculation that we can use actually. So that's how important we need to understand about this fundamental. Okay, so I think that's all for my talk today. Do you guys have any question for me? Is it clear or a little bit complex? If I may ask, I can see on the screen, Brilliant, are you? Is it okay?
Yes, Prof.
Okay. So I will share this slide anyway in the class in the WhatsApp group. So maybe you guys can go through the slide one more time. So then you can try to see whatever area that you don't understand. So we can try to discuss it again in the next class, right? Okay, so I think it's almost time. Is there anything else, Umam?
I think no, sir.
Okay. So if no, I think I got some homework for you guys, right? In the slide just now. I hope you guys can get it. Anyway, I will try to also share the slide as soon as possible. So try to do some calculation from that and submit to me by next week. Okay, so if no, I would like to thank everyone for today and have a good day and have a good lunch. Thank you.
Thank you, Prof.
Thank you, Prof.
Thank you,
Thank
sir.
you.
You're welcome.